All right. Well, welcome everyone. My name is Brooke Smith. This webinar is going to be about designing a cold form steel beam using both AS4600-2018 and AS4600-2005. Specifically, we'll be talking about understanding the design process using the direct strength method. The 2018 and 2005 standard versions are quite similar for the direct strength method. I'll talk about some of the differences, but we'll be actually addressing both in this webinar. So a bit of an outline. I'll be giving you guys an introduction, then talking about how cold form steel as a material is unique for any of you who are unfamiliar with cold form steel as a material. Talk about the changes in AS4600s from 2005 to 2018. And then the meat of this presentation is going to be about designing a cold form steel beam, going through flexural shear, bearing, load interaction, and deflection calculations. We'll go through 2 example beam calculations before concluding and taking questions. So first, as an introduction about me, my name is Brooke Smith. I'm a chartered professional engineer. I originally was trained with a master's degree in the United States, and so I'm also licensed in the United States. Member of Engineers Australia, registered in Queensland as well. I'm currently the lead engineering developer for ClearCalcs. We recently released our cold form steel, also known as light gauge steel, beam and column/stud calculators. So hence we're running this webinar now. I also have 8 years of previous experience, most recently in structural engineering research and development consulting, in which I specialized in cold form steel. I also held a research fellowship in the system behavior of thin-walled steel. And my first job out of grad school was as a forensic structural engineer, examining problems in structures. That's my cold form steel is the area that I am most comfortable in. So I will talk a bit more detail about the material here. So this is going to be the only blatant advertisement slide I'm going to show you guys. We are giving you this webinar for free. But briefly about ClearCalcs. We are a cloud-based platform for structural engineering design. We have a finite element analysis backend, so you can place your supports and loads at any location you so choose and get exact results. Because it's cloud-based, there's no fighting for licenses. And we give you live results as you type, so you can see exactly how every change you make affects the overall results for the design. And because it's cloud-based, we're also available everywhere. So you can work from home, you can work from the office, you can work from the site, you can work from your mobile phone. But back to the main topic here. Today's goals, I want you to be able to walk away from this webinar being able to design a cold form steel beam to AS4600-2018. In order to fit this webinar within about an hour or so time frame, I'm going to make some assumptions along the way. The first is that I'm only going to be talking about C or Z sections bent about their strong or major axis. I'll point out a couple areas where calculations would differ for a minor axis calculation or for other types of sections, but I'm going to only be focusing on C and Z sections. I'm also going to be assuming there are negligible holes in the cross section. Again, I'll point out places where some extra calculation would be necessary if you do have holes in the cross section. Generally, those calculations are additional modifications to the main calculation. So it should be fairly easy to follow along in the standard if you do have holes you need to deal with. We're going to be using the direct strength method. That's clause 7 in AS4600. That's as opposed to the effective width method covered in clause 2 or Appendix D. And I'm only going to be covering detailing on a very broad level. We will be distributing this slide deck and the video of the webinar afterwards. And I do ask, please feel free to ask any quick questions as I go. I prefer to answer questions while I'm still on the topic. Do ask that if you have questions to ask, please use the Q&A feature on Zoom here. Do not use the chat or messaging feature. That just makes it easier for me to keep track of what I have and have not answered. If you do have particularly involved questions, feel free to ask them at any time, but I may wait until the end of the webinar to answer any more involved questions. And just as a note, everything I'm going to be talking about today is based purely on the standards. Cold form steel is my area of specialty. I've done research in it. I know about some of the upcoming research that's likely to be implemented in new versions of the standards. But my intention here is not to communicate any special knowledge. Everything here is purely based on the standard. So first, how cold form steel design is unique. For those of you who are less familiar with the material or more familiar with hot rolled steel or other materials. First off, cold form steel is unique because buckling is a very major issue in the design of cold form steel. Most sections are going to buckle before they yield. That could be local buckling, distortional buckling, or global buckling. Bearing, also known as web crippling, can very easily control a design. That's unusual. Bearing in most materials is generally a pretty easy check, and it's rare for it to actually control. But it must be checked in cold formed or light gauge steel. In CFS, your design may require finite element analysis for actually calculating what the capacity of your member is. In CFS, we are more likely to use the similar finite strip analysis, and I'll talk a bit more about that as we go on. Usually that analysis only needs to be done once for a given section, and it is possible to avoid it as well. And finally, cold form steel is very customizable. Custom shapes may be quite economical. So the design methodology I'm going to talk about here is generally adapted for any type of cross section. So buckling, those of you more used to hot rolled steel may be used to the classifications of a compact, non-compact, or slender section. And there are a few extra calculations that are required if your section is slender. In cold form steel, we essentially assume that every section is slender, and you always need to do every check for buckling. Local, distortional, or global buckling modes are checked. Global includes both lateral and lateral torsional buckling. Stiffeners are used in most cold form steel sections to help mitigate that buckling. The lip that you might see on a C or a Z section is a stiffener in and of itself, but you may also have stiffeners such as what's shown in the photograph in the lower right here, these little dimples in the cross section. Those also serve to help stiffen the flange or the web of your section. Bearing, also known as web crippling, is much more likely to control in cold form steel and does need to be checked anytime that your web is not directly restrained. And that could be at a support or underneath point loads for your beam. In hot rolled steel, those of you more familiar with that, they're pretty simple checks for bearing. It's pretty rare for them to control, but they're much more commonly controlling in cold form steel. And they're also highly dependent upon the precise cross section as well as the arrangement of your supports and point loads. Mentioned finite element analysis. We're more likely to use a close variant of finite strip analysis in cold form steel. But for doing the direct strength method, which is now the more preferred method in AS4600-2018, you need to do a rational analysis. Usually that takes the form of the finite strip method. You generally only need to do that analysis once for a section. Usually it's not going to vary depending upon how long your section is or your arrangement of supports or anything. It's going to, the values you're going to get from that analysis are going to be the same no matter what. There are some alternative methods that exist for obtaining the values, not using the finite strip method, but we're going to be talking about the finite strip method here. Finite strip method differs from finite element in that, those who are familiar with finite element analysis, you may have little squares or triangles representing the shell of a member that you're considering. Finite strip method, you take a strip equal to the length of your member, as shown in the lower left here, and consider how that entire strip is going to behave. And you're going to end up with results that look something like what's in the lower right here. I'll talk more about what exactly that means later on in this webinar, but basically this is telling you local buckling, distortional buckling, and global buckling critical capacities. Cold form steel is also highly customizable, and sometimes those custom sections can actually be quite economical. There are standard sections provided by Lysat, Stratco, FrameCAD, and other manufacturers in Australia. All of those have standard sections that they're going to offer, but you can also produce custom sections as well. Probably not something quite as weird looking as what you see in the lower right here, but custom sections of any types of dimensions you want are possible. So changes since 2005 in AS4600. Big things are that a lot of the old member capacity calculations, what was in clauses 3.3 and 3.4, has been moved primarily to Appendix D. Those were calculations largely based upon the effective width method. The direct strength method, which is clause 7.2 for beams, is now the most complete, really, in the main body of AS4600. The changes since 2005 have also expanded the pre-qualification for direct strength method, essentially allowing the direct strength method with known values to be used for most possible sections you're going to encounter in design. In particular, it's including G500 and G550 steels in the pre-qualification, which are quite common. Further, inelastic reserve capacity is now included within the direct strength method buckling capacities as well. Previously, inelastic reserve was only included in the section capacity for a cold form steel member, but now it's in all of your buckling capacities as well. Shear calculations have also been added to the direct strength method section. It's clause 7. The new shear calculations are adopting exactly what was in the United States standard AS100. There have also been very significant revisions to screws, bolts, power actuated fasteners, and other types of connections. That's outside the scope of this webinar, but those are the main changes since 2005. So direct strength method. As I mentioned, many of those effective width method calculations are now either in clause 2 or have been moved to Appendix D. Previously, you only had distortional buckling calculations in Appendix D. Now all types of buckling are there. The direct strength method is valid for more members, especially G500 and G550. In AS4600, you had several large tables, such as you see on the left, giving you maximum possible dimensions or maximum allowed dimensions in the direct strength method, depending upon exactly what your cross-section looked like. Of note within that, yield strength limits were generally set at 483 or 430 megapascals, which excluded a lot of the modern steels that are used. Now you have a single table for all possible cross-sections, such as is shown in the lower right here. And one of the most important parts of that is now your yield strength is set at a maximum of 655 megapascals. So you're unlikely to have too many members you're going to consider they're above 655 megapascals. Inelastic reserve is now included in all buckling calculations. So there are new sections within clause 7 that talk about inelastic reserve for lateral torsional buckling, for local buckling, and for distortional buckling. And I'll go through exactly what those equations are and say later on. Shear calculations are now included in the direct strength method clause 7. However, fun fact with that, those new equations are mathematically almost exactly identical to the old ones. They're just expressed differently. So for example, your original equation in clause 334 was, given this inequality, V sub V, your shear capacity, is equal to this equation, 0.905 times some factors. Direct strength method, you have a lambda V inequality and a VCR, critical shear capacity here. But if you go through the math on this, pi squared divided by 12 times 1 minus nu squared, those are all constants. That's equal to 0.905. That's where you get that value in the old equations. If you assume that T equals TW, as your thickness for the overall cross-section is the same as the web thickness, which is almost always going to be the same, then AW divided by D1 over T squared is just equal to T cubed over D1. So mathematically, that's the equation you have for VV in old clause 334 is exactly equal to VCR. If you go through the math behind the inequality here for lambda V greater than 1.227, that's also exactly the same thing as the inequality shown there for D1 over TW. So you can actually just use either one of these and get almost exactly the same result. So now for the meat of this presentation, talking about designing a cold form steel beam. So the first step in your design is going to be to calculate your demands using AS1170. I'm not going to go through that. I'm going to assume that either you know that already or are going to be waiting for our future webinar talking about calculating those demands. What I am going to go through is the capacity values to compare those demands to. So capacity is for positive moment, flexural capacity, negative moment, shear capacity, bearing capacity, some load interaction limits, and some specifics for dealing with deflection in cold form steel. So first step is you need to make sure you have some of the geometric values here. All of these are going to be given by manufacturers if you're using a standard section. If you're using a more custom section, you're going to need to calculate these yourself. But you need the effective section modulus about this strong or major axis, a gross section modulus, second moment of areas about both major and minor axis, gross cross-sectional area. The location of the shear center is very important in a cold form steel section. So you need that x naught value. You need your radii of gyration about both centroidal axes, as well as a polar radius of gyration about the shear center. You also need St. Venant's torsion constant and the torsional warping constant as well. So first, you are still going to be using clause 3 for calculating your section capacity. That's based upon yielding and may include an inelastic reserve capacity of its own. Basically, that's your effective section modulus times yield stress, and that's it. If there are several conditions that are met, then you can possibly amplify that with an inelastic reserve. What is inelastic reserve? It's essentially allowing a small proportion of the cross-section to yield in a way that's not going to affect stability, but allows you to get a little bit more capacity than just your pure yield strength. So the conditions there are global or distortional buckling global and distortional buckling cannot occur. We'll calculate that later in this webinar. Fy, the value you use for that, can't include effects of cold forming. When you cold form steel, you introduce a little bit more strength in the steel because of that cold working effect. Usually, most values you see for Fy don't include the effect of that cold forming. So usually this isn't going to be a point you're going to need to think too much about. There's a limit to the slenderness of the web. So dW divided by TW, the depth divided by the thickness of the web has to be less than this ratio. Your shear has to be less than the yield shear. And your web has to be close to vertical, within 30 degrees of vertical. If all of those conditions are met, then you can take your section capacity to be the minimum of either a 25% increase of what you calculated before, or the moment which causes a strain equal to Cy times Fy divided by E. I'm not going to go through the full calculation of that. It's very prescriptive. and requires some additional strain calculations, which can get lengthy. But CY is defined for each element within the cross-section within clause 332. And the phi value for your section member capacity is 0.95 when you have stiffened flanges, 0.9 otherwise, if your flanges are unstiffened. So basically, if you have lips, it's 0.95. If you do not have lips on your cross-section, it's 0.9. So for using the direct strength method, you should be meeting all the requirements set forth in table 7.1 for your cross-section. Most sections you encounter are going to easily meet all of these requirements, but you still should check this. Even if your section falls outside of these limits, you can still probably use the direct strength method. You would just need to calculate your own phi values and make sure that phi is correct for the given cross-section that you have. So for your flexural capacity, your overall flexural capacity is, for the member is defined as M sub B. That's going to end up being the minimum of your global, local, and distortional buckling capacities. First, you calculate your global buckling capacity. There's a lot within all of these calculations. It's going to be based upon the yield moment. So first, calculate your yield moment. That's my equals z sub f times fy. That's based upon the first yield in the cross section. And then you get into your global buckling calculation. M sub BE will be your final global buckling capacity. M naught is the critical global buckling. M naught is the important one here. It's determined analytically. We're going to be determining it analytically, where equations for its analytical value vary depending upon what type of section you're dealing with. You can calculate it directly using the finite strip method, or you can also calculate it using the effective width method. But if you use the finite strip analysis for getting it, you need to redo your finite strip analysis for every possible section, for every use of the section that you have, because it varies depending upon the length and the unbraced length of your member. In general, though, we're going to calculate it analytically. No matter what method you use, you end up going through the set of conditions shown at the bottom of the screen here. So depending upon the value of M naught relative to My, your overall global buckling capacity is going to be equal to M naught. It's going to be equal to My if global buckling can't occur, or this equation if it's somewhere in between. That M naught value I mentioned depends upon the exact section that you're working with. For both a C or a Z section, you can use the equation shown here, CB times A times R naught times the square root of F naught Y, F naught Z. That CB value, many of you will be familiar with from other standards as well. That's having to do with the pattern of moments within the beam. And that equation should look familiar to many of you. M3, M4, and M5 are your moments at your quarter points along the beam. CB, if you don't have that information, can be taken as 1 always, no matter what, conservatively. If you have a cantilever or an overhang that's unbraced, CB has to be taken as 1. And those F naught Y, F naught Z values are the critical buckling stresses for lateral buckling and torsional buckling, respectively. The variables of note in there, LEY and LEZ are your unbraced lengths for lateral and for torsional, for both lateral and torsional lengths. Usually that's going to be just your gross unbraced length, unless you have particularly fancy bracing at your locations. Of note, for a Z section, R sub Y must be based upon the inclined principal axis in this equation. So usually for manufacturer's information, you're going to get R sub Y based upon the vertical axis, based upon the centroidal vertical axis. you can't use that if you're using this equation. You have to use it the inclined principal axis. And there is an alternative equation that exists for Z sections, though, if you don't have the information based upon those principal axis properties. So you can use this equation instead for a Z section. IYC in here is your second moment of area about the centroidal axis, which you're going to get from basically every manufacturer's provided information. L is then the unbraced length, and you should take that as the minimum of your unbraced length for lateral and for torsional. So a couple of questions here. LEY and LEZ are, the unbraced lengths of the beam. Usually they're just a pure unbraced length. If you have a bit of bracing that provides rotational restraint as well, that is essentially a fixed connection versus a pinned connection, then it's going to be unbraced length times a K value. Some of you may remember K times L as your effective unbraced length. So you would multiply in a different K. But in most cases, K is 1. So most cases, effective unbraced length is just whatever the distance is between the different types of bracing. Effective width method, I'm not going to be talking about the details of here. We just simply don't have time within the webinar. So I'm just going to be going through the direct strength method on here. And difference between a lateral and a torsional restraint, that usually a lateral restraint will be a direct connection to the flanges, one or both of the flanges. A torsional restraint is going to be something that actually prevents rotation of the entire cross section. There are examples of the types of bracing for lateral and torsional that are well described and well illustrated in the hot rolled steel standard. Unfortunately, AS4600 doesn't really provide much detail on that. But if you go to AS4100, the definitions are the same for what a lateral and torsional restraint are. So refer to that instead. So moving on. There is now an inelastic reserve capacity that you can use for global buckling as well to provide a bit more global buckling capacity. Again, inelastic reserve essentially allows small amounts of localized yielding so that you actually get a slightly higher capacity than would otherwise be possible. All the inelastic reserve capacity calculations are optional provisions. There are certain types of connections, especially welds, that may forbid you from taking into account inelastic reserve. Obviously, a weld doesn't work very well if the steel underneath that weld starts yielding. So there are certain circumstances where you are not allowed to take this into account, but usually you can. Inelastic reserve can also only be taken into account if your M0 value is greater than 2.78 my. If that's the case, then you can use the equation shown here. The variable you haven't seen yet in here is M sub P. That's a member plastic moment, and that's equal to S sub F times Fy. Now, usually that's not actually given by manufacturers, unfortunately, but it's relatively straightforward to calculate on your own. You calculate it by setting your compression area equal to your tension area and assuming that everything yields, basically as shown in the bottom of the screen here. So then that's your global buckling capacity. Then you go to your local and distortional buckling capacities. For those local and distortional, you need M0L and M0D. Those are, again, fairly equivalent to the M0 calculated through global buckling. Those are most easily determined using the finite strip method, and that's the method we're going to use here. Two of the main programs you can possibly use for the finite strip method include CUFSM, which is free, it's developed by Johns Hopkins University in the United States, or Thinwall, which for commercial uses costs money, produced more locally by the University of Sydney. They both do the same thing. This is analysis, so mechanics doesn't vary from country to country. You can use either for this analysis step here. The critical capacities that you get from these, the M0L and M0D, generally don't depend upon the length of the beam. I say generally because if you have a very, very short beam or extremely well-restrained beam, then one can become irrelevant. If you have a beam that's shorter than about 500 millimeters or so, which hopefully you're not using a beam if you have a length that short, then distortional buckling just isn't going to be possible. There's not going to be enough length available for it. But generally, anything above about 500 to 800 millimeters long is going to have the same M0L and M0D. So I'm not going to go through all of the details of how to do a finite strip analysis. I'll refer you off to either CUFSM or ThinWall or another program you use for your finite strip analysis. The tutorials and references available for those. But I do want to give you a general review of what those results look like, just so you can understand where the values come from for your M0L and M0D. Basically, you're going to get results that look something like what's in the lower right here, where the x-axis is the half wavelength and the y-axis is a load factor relative to m sub y, to your yield moment. Local buckling occurs at the shortest half wavelength. Global buckling occurs at the longest half wavelength, and distortional is something in between. What does that refer to? That refers to the length over which bending will occur within the beam for the particular type of buckling. So one of the easy ways to explain that is just with a basic kitchen sponge. So if I just straight try and bend this, I'm going to get global buckling here. I'm going to get a nice even curve across the full length of this sponge. Essentially, the half wavelength is the length of the sponge here. But if I restrain the sponge globally and try to bend it again, I'm going to get this little dimple in the center here that's only a few millimeters in length. That's local buckling essentially occurring within this sponge. So your local buckling half wavelength is going to form a smaller bend radius than global buckling. And that's what's being considered in this finite strip analysis. So the first local minima you'll see within these results will represent typically your local buckling capacity, critical capacity. The second minima will typically represent your distortional buckling capacity. And after that, you'll have your global buckling capacity. If you are using the finite strip method for calculating your global buckling capacity, then it depends upon length. Because again, your length relevant for that will just be the full length of, full unbraced length of your beam. And that's going to vary depending upon the exact support structure for your beam. However, M0L and M0D are going to be generally the same for a given cross section, no matter what. Once you have those M0L and M0D values, you can make use of those within the calculations in clause 7 in the AS4600. Local buckling in cold form steel terms involves the corners of your cross section staying still while the flat portions of the cross section bend. So something like what you see in the lower right here, where the web and the flange are bending outwards or inwards, but the corners of the cross section are still staying in the same place. That's local buckling. The calculations for local buckling take into account an interaction with global buckling. So hence you have to do global buckling calculations first. Usually local buckling occurs with a half wavelength of somewhere between 100 and 250 millimeters or so. So first step in that is you calculate a local buckling slenderness factor, that's lambda sub L, and that's equal to the square root of NBE, that final global buckling capacity that you looked at before, divided by M0L, value you get from your finite strip analysis. You then take that, and depending upon your value of lambda sub L, the local buckling overall capacity is going to be equal to either MBE or the equation shown here. However, You also have an inelastic reserve capacity that you can make use of in local buckling, similarly as you did for global buckling. If your lambda sub L is less than 0.776 and your global buckling capacity is greater than the yield capacity, essentially if local buckling or global buckling are unlikely to occur, then you can make use of this local buckling inelastic reserve capacity. The calculation of that depends upon whether first yield in flexure occurs in tension or compression. If the first yield is in compression, or if they're theoretically simultaneous, as in most C or Z sections that are symmetric, then you make use of this first equation. You just plug in values. Again, you see the M sub P. This is essentially an amplification based upon the difference between M sub P and M sub Y. If your first yield is in tension, you have a slightly more complex equation here. I'll point out here that there's an M sub YC and an M sub Y. Conservatively, you can always assume that M sub YC equals M sub Y. But if you want to be really accurate here, if you want to get every last bit of capacity you can out of your section, M sub YC is technically based upon the first yield in the compression fiber. If you have a symmetric section, that's going to be the same thing as M sub Y. But if you have a non-symmetric section, such as a C section bent about its weak axis, you might have the cross-section yield in tension before it yields in compression. And so M sub YC will be less than, greater than M sub Y. So just a reminder, if you have questions, please use the Q&A feature and not the chat feature on here. But did get a question of just if the PDFs are going to be available for the webinar. We will be distributing everything relating to the webinar here within the day or two after the webinar completes. Distortional buckling. Distortional buckling involves the corners of the cross-section moving, but where not all the corners move together. So if all the corners are moving together, if they're all moving sideways or all twisting, then that's global buckling. But if only one corner or only some of the corners are moving, then that's distortional buckling, something like what you see in the lower right here, where the entire flange, including its stiffener, are all bending down. Distortional buckling does not depend, or only minimally depends upon global buckling, so we don't take that into account. It's an independent calculation. Distortional buckling usually occurs with a half wavelength of about 400 to 800 millimeters in most cold form steel sections. And it's a similar procedure for calculating that. You're going to calculate a slenderness factor. You note here that it's a square root of M sub Y divided by M naught D, as opposed to MBE. And again, depending upon the value of that lambda D, you switch what the calculation is for M sub BD, your final distortional capacity. But again, you also have inelastic reserve you can make use of for distortional buckling if your lambda sub D, if your distortional slenderness factor is less than 0.673. And again, it also depends upon the nature of the first yield. If it's in compression or if it's simultaneous, you use the first equations here. If it's in tension, you use the second equations here. And same thing with M sub YC versus MY. Overall then, that's all the information you need for your flexural member capacity. The phi value for all types of buckling is 0.90. So then your overall factored flexural member capacity is equal to 0.9 times the minimum of M sub BL, M sub BD, and M sub BE. Minimum of your local distortional and global buckling capacities. So then moving on to shear calculations. Shear is based upon the area of the flat portion of the web. So that's just important. It's a flat portion, so you're excluding the corner radii. It's not the total height of the section. And your first step then is to calculate your V critical, which is comparable in effect to M naught L, M naught D, and M naught that you use in your flexural calculations. But you're calculating this analytically, and your V sub CR is equal to the equation you see here. For unreinforced webs, that K sub V in there is always 5.34. For reinforced webs that have transverse stiffeners, so vertical stiffeners such as you see in the lower right here, then you use a second set of equations where A is the length of that shear panel that you have between your transverse stiffeners. Once you have that V critical, then there are two different sets of calculations you follow after that. One for if you don't have stiffeners, the other for if you do have stiffeners. If you don't have stiffeners, first you calculate your shear yield capacity. That's 0.6 times the area of the web times Fy. Calculate a slenderness factor for shear. That's equal to square root of Vy over V critical. And then depending upon the value of that lambda sub V, you have different sets of equations such that your overall result will be something between your shear yield capacity Vy and your critical shear buckling capacity VCR. Phi factor for shear is 0.9. So then your overall result for your shear capacity is going to be 0.9 times the V sub V value you calculate in here. If you do have stiffeners, similar but not quite the same calculations. Of note, you do need to have at least minimum shear stiffeners. If you have less than minimum, you're essentially ignoring them and you'll use the without stiffeners calculations. You also need to have your spacing between your stiffeners not to exceed twice the web depth. These equations, those of you who are more eagle-eyed here, you'll notice that these equations are essentially identical to what you used for flexural local buckling. You're literally checking for local buckling within each shear panel. So calculate your V sub Y, your slenderness factor for shear, and then switching, but depending upon the value of that slenderness factor between one of these two equations. Again, your overall result, the phi value is still the same, it's still 0.9. 0.9 times V sub V is your final result for your shear capacity. And bearing is particularly important for cold form steel. It's much more likely to control, so you need to actually make sure you do these calculations anytime you have a cold form steel beam. All of your bearing capacity calculations are based upon just one single equation, just the equation shown at the top of the slide here. That equation accounts for the effects of the angle of the web, which is usually 90 degrees, but not always, the radius of the corner of your cold form steel section, the bearing length, and the slenderness of the web. The key to this equation is in all of those C sub x, C whatever, CR, CL, and CW coefficients. There are tables of values that you're going to use to look up what all of those C coefficients are, and different tables for C sections, Z sections, built-up I sections, hats, or steel decks. Of note, the equation here and all the coefficients in those tables are per web. So if you have a box section, if you have nested Z's, if you have anything else that's going to give you multiple webs over one bearing location, then you would multiply this by 2 or however many webs you have. Also, phi sub W, your phi factor for bearing, is not a constant. That has to be looked up within the tables as well. So what are these tables? An example for C sections is shown here. They're fairly large tables for which you would figure out what row of the table is relevant to you and pick out your C, CR, CL, and CW and VW values. So for these, you need to know whether your beam is fastened or unfastened to the support or load or concentrated load. You need to know whether your flange is stiffened or not, generally whether it has a lip or not. And you need to know whether it's one flange loading or two flange loading and whether it's an end or an interior location. So you may have different bearing capacities for different supports and different concentrated loads along your beam. But what does one flange and two flange loading refer to? That refers to if you have a support that is very close to a concentrated load. So if you have a concentrated load directly above the support, both of those are going to be acting together, and you're going to have a slightly lower capacity for your web crippling, for your bearing. The limit for that is 1.5 times the height. So if your concentrated load is less than 1.5 times the height distance away from your support, you have two flange loading. If it's greater than 1.5 times the height, it's one flange loading. The diagram you see on the right here illustrates this graphically. I took this from the United States standard, but it's exactly the same provisions. And an end or an interior location refers to generally whether your support or concentrated load is within 1.5 times the height of the end of the beam, or whether it's greater than that. There are some additional limits to the validity of each of these rows. That's your corner radius divided by the thickness of the web. That's your last column here. You are supposed to be meeting these. Got a relatively lengthy question. I'm going to save that until the end of the webinar here and go over that at the end of the webinar. For Z sections, you have a similar table as well. A note I'll make for both of these tables, not all possible conditions are always covered by these tables. So for example, if you have an unstiffened flange that is fastened to the support, there is no row specifically for that. If you have that type of situation, use the more conservative of the options. So an unfastened flange that is fastened to the support, just use the unfastened, unstiffened flange rows. They're relative to that. They're relevant for that. So then load interaction. You have interaction between flexure and shear, and you have interaction between flexure and bearing, both of which need to be checked. The interaction between flexure and shear depends upon whether you use shear stiffeners or not. If you don't have shear stiffeners, you use the equation at the top of the screen here. That's your demand divided by your factored capacity, sum of squares for your moment and your shear. That has to be less than or equal to 1.0. With shear stiffeners, you have a slightly different equation as shown on the second line here. Of note, you only need to use this equation if your demand is greater than half of the overall capacity for a moment, and if your shear demand is greater than 70% of your shear capacity. Of particular importance here, the M sub S is not the same M sub S that you calculate in clause 331. It is instead an M sub S equal to M sub BL, equal to your local buckling capacity, but without considering global buckling interaction. So essentially, you're going to recalculate M sub BL such that your local buckling slenderness capacity is equal to the square root of M sub Y divided by M naught L. That's as opposed to the original equation, which was M sub BE divided by M naught L. So calculate lambda L, switch which equation you use for your local buckling capacity, depending upon the value of that lambda sub L, and you cannot include inelastic reserve in that calculation. So essentially, the M sub S in here is equal to your local buckling capacity, but using M sub Y instead of M sub BE, and not including inelastic reserve capacity. Additionally, though, if you have web stiffeners, that is, if you're using the second equation here, you need to take your M sub S equal to the minimum of the local buckling capacity, as shown here, and the original distortional buckling capacity. You don't need to take into account distortional buckling capacity for the first equation. So I know it's a bit complex, but yeah, just make sure that you do not use the same member section capacity as in clause 331. So then flexure and bearing. This applies, again, for both concentrated loads at supports. So when there's typically a negative moment interaction with the support, and for point loads, typically a positive moment interaction with the point load. So a few different equations here, depending upon the type of section you have. If you have unreinforced single webs, you use this first equation. There is an exception that exists for if you have members spaced less than 250 millimeters apart, and you have lateral bracing, such as a deck or floorboards or something like that, bracing the top flange of these members, then you do not need to take into account flexure and bearing at all. However, that's a very specific exception, and again, only for maximum spacing between the webs of 250 millimeters. If you have back-to-back C-sections, you use the second equation here, and if you have nested Z-section, you use the third equation. Slightly confusing again with this. For the first two equations, you're using your phi sub W and phi sub B that you had from your original bearing and web crippling or bending calculations. For nested Z sections, phi is always equal to 0.9 for all the occurrences of phi in that equation. There are a number of additional connection and geometric restrictions for that nested Z section calculation. I'll refer you just to look at clause 337, see if you have nested Z sections you need to consider. There is something a bit confusing still in the AS4600-2018 revision in that flexure and bearing interaction equation. That is that the definition of M sub S is different for the different equations. For the first two equations, for that single web C-section and for the back-to-back C-sections, M sub S is the value that you calculate in clause 331. For nested Z sections, it can be either the value you calculate in clause 331 or the M sub BL that we calculated for the flexure and shear calculation. The reason for that difference, I can tell you, is because the first two equations were originally sourced from AS4600, originally sourced from Australian research. The last equation for those nested Z sections is taken straight out of the US's ASI S100. S100 allows you to always use that M sub BL value, but because the research did not originally include the direct strength method for those first two equations, M sub S is not allowed to use that value. So basically, make sure you're paying attention to what M sub S should be for the specific type of section that you have, and be very careful of those definitions. Hopefully that will be cleared up in future versions of AS4600, but for now, just be very careful of those definitions. And finally, deflection of your cold form steel beam. There is an important difference in cold form steel between the effective and the gross moment of inertia. Manufacturers, if you're using a standard section, will always give you an I effective. You can always use that value. It's going to be conservative in many cases, but you can always use that. If you want to be a little more accurate and a little less conservative, you can use the equation here to calculate what I effective is based upon a scaling of the gross moment of inertia. So for this, your capital M in the denominator there is the moment demand due to your service loads that you're considering. So whether that be permanent and imposed loads or just permanent loads or whatever you're using for your service loads, set that equal to the moment that's going to result from that. And your M sub N is equal to M sub B, the same flexural capacity that we calculated earlier, except you're going to go through and completely recalculate that M sub B, replacing every instance in our calculations where you have M sub Y with M instead. So you're replacing your yield moments with your service moment. and recalculating M sub B, recalculating your member flexural capacity. So it is a fair bit of calculation work, but it's going to give you less conservative value to use for your deflections. And if you're hitting your deflection limit, you probably want to make use of this. What can help you a bit with cold form steel is we can assume that your stiffness is equal to 203,000 megapascals rather than the traditional steel value of 200,000 megapascals. So you get a slight boost in stiffness because of that. So wrapping up our beam design, this represents everything we went through, the general requirements for cold form steel beams. There are a few alternative equations you can make use of, which will generally give you a little bit more capacity for specific types of systems that you have. If you have beams with one flange through fastened to deck or sheathing, refer to clause 3334 for a modification factor for that. And if you have one flange through fastened to a standing seam roof, then you can look at clause 3335 there and get a modification factor for that as well. I'm not going to go through those calculations. They're pretty straightforward. But if you have one of those specific systems, just refer to those sections and you can get potentially a little bit more capacity out of your system. Most of the detailing requirements for cold form steel systems are contained in clause 4 of AS4600. Those will be things like minimum spacing of torsional restraints and what qualifies as different types of bearing restraints and how you calculate forces in those restraints. So now going on to some example calculations for beams. Our first example we'll make use of is a simply supported beam. This is one of the simplest examples you can make use of. We're going to assume that it only has permanent load and imposed load, a G of 0.2 kilopascals and a Q of 1.5 kilopascals. We're going to assume it's just a 3-meter beam. Assume it's an office building for the purpose of the character of the imposed load, 450 millimeter load width. We're going to assume it does not have any transverse shear reinforcement, that the top flange has bracing at 500 millimeters, and that there's torsional bracing only at the very ends of the beam. So the full span length is equal to the torsional brace length. We'll use a C100-15 section. That's a section produced by both Stratco and Lysat. The first number in there is the nominal height of the web. So it's actually 102 millimeters, nominal 100. The second number in there, 15, refers to the thickness of the web, of the entire cross section. So 15 is 1.5 millimeters. For this type of section, your flange width is 51 millimeters. We'll use ClearCalcs as our means of providing this example. So I'll open up my web browser, go to clearcalcs.com, and log in. We'll create a new project, just call it webinar here. First project for webinar clients, let's say. And I'll add a calculation for a cold form steel beam. We have a number of choices for different types of cold form steel beams. These just give you different default loads and default support conditions and default restraints, depending upon exactly the type of beam being used here. We said this was a floor system, so I'll select floor joist in this case. So that'll open up our design sheet here. We said that the total length is 3 meters or 3,000 millimeters. And page loaded there. Top flange bracing is 500 millimeters. And we said that the bottom flange bracing and the torsional bracing would just be equal to the total unbraced length of 3,000 millimeters. Simply supported beam, so we have restraints only at the start and end of the beam. Said permanent load of 0.2 kilopascals, an imposed load of 1.5 with a load width of 450 millimeters. a character of imposed load. This is an office building, we said, so it's floor office. By default, we're including the alternate imposed load, which AS 1170.2 calls for. For simplicity of the analysis here, I'm just going to remove that from our calculation, just to make the graphs here make a bit more sense. But so then you see we are still on a C150-15. We're using a C100-15 section for this calculation. So from that, we get our overall results here. Positive and negative moment demands and capacities with our section capacity and the member capacities. Shear demand and shear capacity. We are allowing you within our calculation here to include members with holes. I say I did not go through all the details of those calculations within this webinar, but you can include that in our calculation sheet here. The bearing or web crippling demand capacity, and then bending shear and bending bearing interaction values as well. Our most closely governing value here is deflection, where we have a deflection of 9.2 millimeters with a limit of 10 millimeters, so just within our allowed limits. We have all of our charts here showing the shear, moment, and deflection. By default, we're showing you the governing load case, which is 1.2 G times 1.5 plus 1.5 Q. We can select other possible load cases here, such as 1.35 G, and that will refresh and show a lower value within the envelope. Or we can also look at individual loads alone. So looking at live load alone, you can see the moment and shear that results from those, as well as the deflection that results from live load alone. So for a simply supported section, if you want to assign a moment connection to both ends, such as if you have a fully fixed section, then we allow you to just select simply pinned or fixed for support type. You can also apply a concentrated moment within a table here if you have a moment that you're applying as well. And as to what constitutes a moment connection for a cold form steel beam, 2 bolts with a cleat would definitely be considered simply supported. This is engineering judgment as to what you would consider to be a fixed connection. The questioner here asks if 4 bolts within a single member at the end might be considered a fixed connection. My opinion as an engineer is yes, probably it can be, but that's your call as a professional engineer to decide whether that would be considered a fixed or pinned or something in between connection. All right, so that is our first example. Let's go back to the presentation. And for our second example, we'll have a more complex beam here. We'll have multiple supports, still keep them as pin supports, but we'll have the same loading, 0.2 and 1.5 kilopascals for permanent imposed loads. But we'll apply that over the full length of the beam. So the total length of the beam will make 10 meters, with 2 meters between the first 2 supports and 5.5 meters between the second 2 supports. That leaves us with a 2.5 meter cantilever at the end. Same assumptions we'll keep for simplicity here of an office building, floor purlin, no transverse shear reinforcement, keep the load width the same. We will add some additional bottom flange and torsional bracing at 1 meter on center spacing. And we will need to use a slightly bigger member for this. We'll use a C150-19 for this design. So for doing that calculation, for simplicity, I'll just duplicate the existing calculation that I have here. and just modify that. So we said this was going to now be a 10-meter beam. We can use simple formulas in here. So I'll just say 10 times 1,000, 10-meter beam. And that will do the calculation for that. We said that bottom flange and torsional bracing would be 1,000 millimeters spacing. We're keeping the same top flange bracing at 500 millimeters. This time we have supports at 2,000 millimeters and at 7,500 millimeters. We'll keep the same bearing length of 25 millimeters just for simplicity again. Our loading parameters all stay the same. And as you can see here, the existing section, C115, is insufficient. We get failures in our moment capacity, in our moment and bearing interaction capacity, as well as in our deflection. But we can get a quick view of what works and what doesn't by opening up the member selector here. So in this case, we're going to look and see a C115-19 is a fairly efficient section that works. And we can see that that opens up and shows us a working section. We can additionally load link in our other beam here. So say that our other beam is resting on top of this beam. I can load beam B1, select it here, and put in a location for it. Let's say at 4,000 millimeters. And you can see how that modifies then our graph here. We're still showing the live load alone, so hence all of our graphs show an intermediate value within the envelope, within the load case envelope. And we do check all load cases simultaneously here. So if you want to see individual load cases, you can open up charts here. You can see every strength load case, the shear moment and reaction that results from each of those. You can see the unfactored load values. We only have permanent imposed loads here, so all other types of loads have 0 results. And all of our calculations for member section capacity, member moment capacity, all contained within all of the subsections here that you can open up. Global buckling, for example, we can look at more detail on this as well. We can see that our global buckling capacity, we are using the first of the equations in the conditions. Our M naught is greater than 2.78 times My. So we're using My. And we can see the references for these equations. Right now, this sheet is still using AS4600-2005. We'll be updating it to 2008 by the beginning of next week. And similarly, you can open up everything else in here, see exactly what equation is being used. Our distortional buckling capacity is making use of the more complex equation for distortional buckling. And similarly for all of our shear capacities, our bearing capacities, in this case, you can open up bearing capacity and see a table of all of the different types of bearing that exist. So our first support is an end condition, bearing type 1 on this table. And the other supports are interior conditions, labeled as bearing type 1.1 on this. You can see the reactions that occur at each of those, the capacities for each of those locations, and the overall demand capacity ratios. And again, everything's summarized over on the right. So a question of whether the added beam that we put in there for B1 is providing lateral bracing. The calculation on this sheet right now is basing all of its basing all of its bracing calculations upon the first table that you have here. So assuming your lateral bracing at the top flange 500 millimeters, the bottom flange 1,000 millimeters, and torsional 1,000 millimeters. We don't currently let you, within our calculations, set what the specific locations are of the bracing. We're just taking the maximum worst case values. But typically, if you are connecting a beam there, you are going to have lateral bracing. All right. So then just going back to our presentation, those are the two examples I wanted to show there. And now I'll just conclude and take any more involved questions that you may have as well. So summarizing everything, cold forms engineering design is unique compared to most other materials because of the importance of buckling, because of the importance of bearing, which is much more likely to control in cold form steel than in other materials. The fact that you're making use of a finite strip analysis, which you don't typically need to do for most other materials. It's usually purely analytical hand calculations for most capacity calculations in other materials. And the fact that cold form steel is very customizable in shape. So your cross sections can take on very custom designs as you see fit, in addition to more standard cross sections that are available from many of the manufacturers. The changes since 2005 in AS4600 include a bit more of a focus on the direct strength method, particularly the inclusion of G500 and G550 steels in the pre-qualification for direct strength method. We're now including inelastic reserve capacity within the direct strength method within each of our types of buckling. And we've added some shear calculations, even if they are mathematically basically identical to the original ones. We went through all of the full process for designing a beam, including checks for flexure, shear, bearing, load interaction for both flexure and shear and flexure and bearing, as well as deflection, keeping in mind our difference between effective and gross second moment of areas. And we also performed two different examples calculations there, one with simply supported beams and one with complex beams. So at this point, if you have any other questions, please feel free to ask them. Again, please use the Q&A feature on Zoom here. In the meantime, I do encourage anyone who enjoyed this webinar to keep an eye out for future free webinars, which we'll be offering for the design of other types of members and connections. Within the ClearCalcs platform, we already have available timber, steel, cold form steel, concrete, several different types of connections, footings, as well as post and sleeper retaining wall calculations. And in development right now, we have several other more advanced calculations for connections for other types of foundations and other types of retaining walls as well. All right, well, thank you everyone for your time. If you do have other questions, please feel free to email me. You can contact me at brooks.smith@clearcalcs.com. My contact information will also be included in the email you'll receive after this within the next day or two, including the webinar recording and a full copy of the slide deck. Yeah, please feel free to contact me with any other questions. And thank you very much for attending.